Okay, students, hopefully this video has audio. So I am re-recording the Chapter 7 video. The focus of our lesson for the next test deals with linear programs. This area of operations is very important to managers, particularly in logistics and supply chain management, but it is also useful to anyone who wants to optimize for some business function. In general, when we are optimizing, we will want to either minimize cost or maximize profit. This will be evident in our objective function. What prevents us from making infinite profits are our constraints. We will be looking at making a decision based on solving a system of equations. In the first example, you are a manager of a furniture company and you want to make as much money as possible. Thus, your decision is based on whether you should make tables or chairs and how many of each. So, in this chapter, we mostly focus on a set of problems called the product mix problem. However, in Chapter 8 and Chapter 9, we will talk about different applications that we can still utilize linear programming on. We will want to focus on what our limiting resources are. Often it is time, or money, or our resources needed to make the product. Ultimately, we will want to know how much of each product to make such that we maximize the amount of money we can make for our business. So our first example is the Flair Furniture Company. It's the first example in the book. The Flair Furniture Company wants to know how many tables and chairs they need to make to maximize profit while being constrained on the number of available hours in two departments, painting and varnishing and carpentry. So we're given a set of constraints and our objective function in this word problem format. And what we want to do is convert that into something we can solve. So one way is we can put it into a table where we can line up our limiting resources here, which is hours in a week that we can use to do our two functions, carpentry and painting and varnishing. Now, the way we read this is in the carpentry department, it takes 4 hours to make a table and 3 hours to make a chair. And then to paint and varnish those takes 2 hours to make or to paint a table and 1 hour to paint a chair, and we're limited by the amount of hours in a particular week. Our objective function comes from these two values. It's how much we can sell each of these items for. So our objective in this problem is to maximize profit. And if you look at the bottom, our decision variables are the number of tables to be produced each week and the number of chairs. So we're trying to make a decision on how much of each of those to make in order to maximize our profit. Now, that's subject to the constraints here in the middle. We're limited by 240 hours of carpentry and 100 hours of painting and varnishing. So to create the objective function, we want to maximize our profit of whatever our profit is for a table plus whatever our profit is for a chair. Then we want to develop a mathematical relationship for our constraints. So we know it takes 4 hours to make a table, and then we're going to multiply that by the number of tables we decide to make after we optimize our system of equations. And then we're going to add to that our 3 hours to make a chair times the number of chairs. And then our limiting resources is the number of hours that we have in each of those departments. So second constraint on painting and varnishing, we want to look at our left-hand side. Painting and varnishing time actually used is going to be less than or equal to the painting and varnishing time that is available. So to read this, we have 2 hours of painting and varnishing to make one chair, plus 1 hour of painting and varnishing, or to make one table, plus 1 hour of painting and varnishing to make one chair, and we're limited by 100 hours. Both of these constraints have to be cannot be violated. Well, neither of the constraints can be violated in order for us to find our optimal solution. So we also can't make negative chairs or negative tables. Thus, we put our non-negativity constraints, which basically gives us that value. So the 4 parts to our linear program is we define our variables, we have our objective function, we have our set of constraints, and finally our non-negativity constraint. And that is the 4 parts of a correct answer. So the way I like to do it is you always define your variables first, then you put your objective function, then the constraints that you have, and you can have 1 to basically an infinite amount of constraints for a linear programming problem. And it's always best to end with non-negativity, even if it's redundant, because if you don't put it and it needs it, then you can end up with negative values, which will give you the wrong answer. So we next move on to graphing linear programs. That's the easiest way to solve small problems with 2 decision variables. The other advantage is because of non-negativity constraints, we're always working in that upper right quadrant on our Cartesian graph. So because of non-negativity, when we make 0 tables, it keeps us on this axis. And when we make 0 chairs, it keeps us on this lower axis. The first step we want to do is identify the feasible region. So we'll plot each of our constraints on the graph, and that will give us this convex figure of all the feasible solutions to our problem. So let's start with the first carpentry constraint. So we plug 0 in for t, then we will get 3c equals 240. So we should get c equals 80, and that'll give us 1 intercept. We do the same for the other, or if you put a 0 in for c, we will get 4t equals 240, and then we should get t equals 60. So we can see that here. By plotting the 2 intercepts, makes it easy to graph the line for our carpentry constraint. Now if we just examine the carpentry constraint and we have the feasible region created by that constraint and our non-negativity, we can see that this point here is a feasible solution, but we know that it's not an optimal solution because we can continue moving to another point that will have a higher maximum profit. We know that a point that is outside of the feasible region is not a feasible solution. Now, generally, the optimal solution is going to be somewhere on the line, usually at a corner point. This particular point, 30, 40, I'll come back to in a second. We plot each of those points into our constraint. We can see that at that point, it exactly satisfies the constraint. We have 240 hours, and we use 240 hours. The point below that line that is a feasible solution, we plot that point in, then we use only 180 hours, but we had 240 hours available, which means we have 60 hours of slack, and thus there's likely a better solution. However, in the last one, we only had 240 hours, but we're trying to use 400, and thus we violated a constraint, and that's why it's not a feasible solution. Now, we can plot our other constraint, the painting and varnishing constraint. We plug in 0 to find our intercepts for each of those variables, and we can plot that constraint and develops another feasible region. But to solve our problem, we need to know what the feasible region is that takes into account both constraints. So we'll produce a new graph with both constraints. Now we see that we have this convex figure. It's going to have 4 corner points, and this is going to create our feasible region here that takes into account both of the constraints. So now we plot in those same points. this was the point that was in the feasible region. It doesn't violate either constraint and thus is a feasible solution, but it's not an optimal solution. This point was outside of our feasible region and thus violates both constraints and is not a feasible solution or an infeasible solution. We can also have points that are in our feasible region that will satisfy, or if it's in our feasible region, it should satisfy both. But in this case, we have one point where it satisfies one constraint but not the other. So when we actually want to go find the optimal solution, we can use two methods that we're going to talk about. The first is the ISO profit line. We start with some possible profit value and we set that equal to our objective function, which will give us a line of a certain slope. Then we increase the value of our objective function until we touch exactly one point in the feasible region. Usually it's a corner point. So we arbitrarily pick the function or the value 2100 and we plot that line. So that's here. Oops. Over here. So we know that because we can still increase this and remain in the feasible region, we can go higher than this number. We set each of those, or we increase that value until we get to a value that touches exactly one point of the feasible region, and that will be our optimal solution. And we know that it is at the point 30 tables and 40 chairs will produce a maximum profit of 4,100. Now, I find the corner point solution method to be better. This uses mathematical theory to find the corner points in that figure, and then you plug them into the objective function, and then you pick the highest one. So here we had 4 corner points: the origin 0, 0, 0, 80, which was one of the intercepts, 50, 0, which is the other intercept, and then we have where our two constraints intersect. Now we've talked about a few different ways you can find the intersection of two lines. You can use this elimination method, where if we multiply the first constraint by, well, if we multiply the painting constraint by -2, then we can cancel out the tables. Then we take 3c minus 2c equals 1c equals 240 minus 200, which is 40. So now we know that c equals 40. You go back and you plug it in to the constraint. So we substitute the c here with 40. We multiply that out to get 120. We continue to solve that out, and then we get t equals 30. Thus, we can get the corner point of 30, 40. Now, that intersection is not always going to be the optimal solution. It really depends on the slope of your objective function. So we'll talk a little bit about that later in the video, though. So, like I mentioned a little bit earlier, slack is the amount of resource that is not used in a less than or equal constraint. So when we only used 155 hours of carpentry, but we had 240 available, then that means we had 85 hours of slack. And generally, if you have slack left in your resources, then you're not at the optimal solution. So at the optimal solution, the slack should be 0, as all of the 240 hours were used. Surplus, on the other hand, is used with a greater than or equal to constraint, and that indicates the amount by which the right-hand side of the constraint is exceeded. So if we have this other new constraint that says tables and chairs have to be greater than or equal to 42, if we had a total of 45 chairs that we made, that means we have a surplus of 3 chairs. This tends to be more of an effect in a minimization problem. So this kind of summarizes the two methods for finding the solution to a linear program. The next step is, now that you have a solution, many managers will want to ask what-if questions to see how they might be able to manipulate that decision to improve it. So let's look at an example. So we have this St. John Pottery Company. They make bowls and plates. So we have 40 hours of labor and 120 pounds of clay to make these bowls and plates. We have our profit here. We could sell a bowl for 40 and a plate for 50. To make one bowl requires 1 hour of labor and 4 pounds of clay. To make one plate requires 2 hours of labor and 3 pounds of clay. So our formulation looks like this. We have x1 is our number of bowls, x2 is the number of plates. Our goal is to maximize profit of 40x1 plus 50x2. We have our two constraints here. First is the number of hours of labor. The second one is our pounds of clay. Finally, we have our non-negativity constraint. Now I want to quickly show you how to use Excel to set up or use Solver to solve the problem for us. So we can pick a random cell and we're going to assign that to our decision variables. And so our decision variables are going to be x1 and x2. So say x1, x2. But these blank cells are going to be what represent those variables. The next set we need to make is for our objective function. So we put the coefficients of each of those variables here. So here it's 40 for x1 and 50 for x2. Now the goal for this particular problem is we want to maximize our profit. So going to create another box here that's going to represent what our final solution is. So we're going to use a new formula called sum product to create that equation. So we're going to use this vector, which is a vector of our two decision variables, times a second vector of their coefficients. You could also, if you don't want to use sum product, it is equal to our variable times its coefficient plus this variable times its coefficient. Okay. So what this says is the blue box times the red box, so that's 40 times x1, and then this purple box times the green box, or 50 times x2. But it'll give us the same answer as using sum product. Okay, the next step is to put in our constraints. So anything in this column represents x1. Anything in this column represents x2. So our first constraint was labor. We have 1 hour for a bowl and 2 hours for a plate. And you're limited by 40 hours of work. And this is going to be our right-hand side, and this is going to be our left-hand side. Our second constraint is the amount of clay we have. It takes 4 pounds of clay to make a bowl and 3 to make a plate, limited by 120 pounds of clay. We're going to use that same sum product formula, or you can multiply it out. But we want to make our decision variable and we want to multiply them by those coefficients. And do the same thing for the second constraint. Multiply the decision variables by their coefficients. Now the reason we set it up this way is to make it easier to put into solver. So we're going to say that the left-hand side has to be less than or equal to the right-hand side. Now, if solver should be on your data tab, if it is not, then you will go to File, and then to Options, Add-ins, and then you go to Excel Add-ins, and you hit Go, and then you check this solver add-in, and then it should populate here. Now, what we want to do is select each of the cells. So our objective is going to be here, and H4 for me, but it's whatever our max profit is. It's the objective of our problem. This is a maximization problem, so we'll select max. By changing variable cells, that's our decision variable. So it's going to be these two cells here. E4 and F4 for me. And it's subject to the constraints. So we'll add, and then because these are both less than or equal to, we can highlight both these cells because they're both left-hand side and they're both less than or equal to, which is where here, where we could change it. And then we're going to put our constraint right-hand side on the other side. So that's the easy way to put our constraints in. Non-negativity is already checked. We want to change this to simplex, and then you hit solve. And what it will do is it will give you the max profit, the number of bowls you should make, and number of plates you should make. So that's how we would solve that problem using Excel Solver. Now the next step is we have our optimal solution, right? 24.8, the max profit of 1360. So now we want to ask those what if questions, and that's really what sensitivity analysis is all about. Well, what if we had 50 hours of labor instead of 40? How is that going to affect our decision? Or what if we had more clay or less clay? Or what if we decided we wanted to sell our bowls for 60 instead of 40? Those are the kinds of questions that a manager would ask, and this is really why linear programming can be useful, even on this small scale. So the first question is, will the optimal solution change if the objective function coefficient per bowl changes from its current value of 40 to 30? So maybe we decided that the bowls, trying to sell them for 40 was too much, and maybe we can only sell them for 30. So take a look at how those two graphs change. What you'll notice is that this is our optimal solution. So the black line represents our objective function at that particular value. Go through that corner point, and that's the optimal solution. What we notice is that the optimal solution doesn't change. We're still going to make 24 bowls and 8 plates. So let's look at another one. Will the optimal solution change if the objective function went from, or for the price, or what we can sell a bowl for changes from 40 to 25? So we further drop that price. And what we see is now have a situation called multiple optimal solutions. Basically anything from this corner point to this corner point will be the optimal solution. Will give us the same value. Based on how the simplex method works, though, our optimal solution doesn't actually change because it would still be this point. So now let's further drop that objective function coefficient per bowl from 40 to 20. So now we've dropped it to 20. But now pay attention to this objective function line. Now it no longer touches this corner point, and we've actually moved to the other corner point, and thus our optimal solution will change. Now we will make 20 plates and 0 bowls, as opposed to where we were over here, we were going to make 24 bowls and 8 plates. Well, we will find that here by pulling the sensitivity report in Excel. And you will see this report, which we're going to explain now. So our original problem, we had the objective function for bowls, the coefficient was 40. But what this report tells us is that we can increase this value by 26.6, which means 66.6 or below, or we can decrease 40 by 15, which would make it 25. That gives us a range at which this optimal solution will stay the same. We can continue testing that. So what if we increased what we can sell a bowl for from 40 to 60? We see the slope has changed objective function, but our optimal solution stays the same. However, if we raise the price that we sell a bowl for to 80, now we've moved off of that corner point to our other corner point. So now we would make 30 bowls and 0 plates. So that's where this range comes from. 80 was higher than 66.6, and when we've gone beyond that number, then our optimal solution, which is displayed here, is no longer correct. And we would have to adjust our spreadsheet to get a new set of answers. Now we can do the same thing for plates. So if we decrease the amount we can sell a plate for from 50 to 40, will it change the optimal solution? And you can see on the graph, no, we are still on that same corner point at 24.8. We continue to lower it from 50 to 30 for what we can sell a plate from. We see that we get another occurrence of multiple optimal solutions. So now any point between here and there is an optimal solution. But technically, we have not moved off of that point, so the solution stays the same. However, if we lower what we can sell a plate for from 50 to 25, then we change the corner point that we are on, and now our optimal solution changes based on that value. So the original coefficient was $3 was what we could sell a plate for. If we lower that by 20 to 30, anything below 30 will change our optimal solution. Now we can do the same thing where if we increase the profit for what we can sell the plate for from 50 to 60, it doesn't change our optimal solution. When we change it to 80, then we get a situation of multiple optimal solutions. And if we continue to increase it, then we should move to the other corner point, and thus our optimal solution will change. And it all comes to the bounds that we have set based on our objective coefficient. We can increase it by 30 or decrease it by 20, and we will still remain on this optimal solution. Once we exceed those, then our optimal solution will change, and we'll have to look at what the new solution will be. So the next set we're going to look at is the effect of changing the right-hand side. So I said before, what if we currently work 40 hours a week, but we want to see the effect on our profit if we are able to increase our work by 10 hours. So if we worked 50 hours a week, how would that affect our optimal solution? And the answer is yes. We have moved from our point 24.8 somewhere over here, and we've changed the slope of this line. We've actually increased the slope such that our corner point has moved, and our profit has increased because now we have more hours to make bowls and plates. Second question, will the feasible region change if we increase the amount of hours from 40 to 50? And yes, of course it will, because we've changed our constraint. The feasible region has gotten bigger. We've added more resources to our problem. So what the right-hand side has to do is something called shadow prices, which is a special value that tells us if we increase a resource by 1, how much our profit will increase. In our current example, if we have 1 additional hour of labor, how much would our profit increase? We can see that in our table here. It's on our sensitivity report. That's what our shadow prices are. What this says is that if we had 1 more additional hour of labor, then we would increase our profit by 16. So if we had 10 more hours of labor, then we would increase our max profit by 160, because it would be 10 times that. So, but we also have the same bounding issue here. We can increase our right-hand side up by 40, so we could have a maximum of 80 hours in which we could continue to increase our profit, or we could decrease our number of hours by 10 before these shadow prices would change. So we can look at that bound. Will the shadow price change if the amount of hours increased from 40 to 85? And the answer is yes. So what's happened is we've utilized all of our hours, but it's no longer the limiting resource. We can't increase our profit anymore with hours alone. And what's happened is now we've used up all of our clay. So we could continue having more hours, but it will not increase our profit because we've run out of clay to actually make the bowls and plates. The last set of possible sensitivity analysis is the addition of a new constraint. And what this constraint says is, what if we said you cannot make more than 32 bowls? Well, it's kind of a redundant constraint, because as long as it says that, our optimal solution is still the original solution. The feasible region stays the same, so it really doesn't affect our analysis. However, if we look at the flip side of that and said we have to make at least 32 bowls, now there is no feasible region for us to find a solution, and thus now the answer would be no feasible solution. Okay. So hopefully there's sound on the video.